Image segmentation was historically hard manual work. You sit down on one of those assisted mask generation software like Rhythm and you go clickety clack to create a base dataset of masks to fit your use case. In today's deep dive video, I'll show you the methodology that Meta used to start a segmentation foundational model called Segment Anything. This new methodology, inspired by a large language model, unlocks a new type of model that is able to execute many segmentation tasks in zero shot just by being prompted properly. For those that are new to the channel, I'm Yassine, a published researcher and machine learning practitioner who love to teach. The methodology is segmented in three main areas: the task, the model, and the data. We're going to go through these along with the results and limitations of the original SAM technique. So throughout this video, I'll be using UPDF, who are kindly sponsoring this tutorial. So UPDF is a PDF editor by SuperRay Software that was founded in 2021 in Shenzhen. So it's quite cool that there are a company out there that are wanting to sponsor a very technical tutorial like this one. So big thanks to them. To be honest, I found it quite useful to annotate this research paper and scribble around them with notes that get edited straight into the PDF. They even offer offline mode if you aren't too keen on having your paper hosted in the cloud. Check out the links in the description for more info and to get a free account. Let's get started with the task and requirements that the author used to design their segment anything model. So the other were mainly trying to develop a promptable model in there that was pre-trained on a broad dataset using like a task that enabled generalization. You have the prompt and then you have the image and then you have the mask. Like that's kind of the rough idea. It always output the mask and it can accept like a wide variety of prompts. So it can accept points in here. It can accept like boxes, so top left and then bottom right coordinate. It can accept literally another mask. It can accept text. So the idea is that you could give any of this and then the model should be trained in a way that it will always output a mask. So this is very similar to how a large language model like generative pre-trained transformer have been conditioned. So with this setup, they can then have like a whole slew of downstream tasks that they can compose the model with. As you can see over here with all these like hand-picked images with the mask, we have a wide variety of masks of various sizes. We have over here the mask, the image with like less than 50 masks, so it's big, bulky masks that we're applying. And then you can get like up to the 1,000. Like look at this one. Like this one is absolutely crazy. And the segmentation looked pretty good. Same thing with this one. It's very, very fine details and it still works. So this particular setup allowed the model to gain like zero shot performance on multiple segmentation tasks without requiring any additional training. Like with the single point valid mask evaluation, like this was zero shot on a new dataset. With the edge prediction, this is like a very old computer vision task. With the object proposal, it's a bit more mid-level. With the instance segmentation task. And finally, one that's a bit more experimental, which is the text to mask. So basically you input what you want to segment in plain English and the model will like segment it properly. Now, the research motivation are all nice. This is Meta, so their research kind of need to be tied back to a business objective. So for this specific project, it's quite easy to see what it would unlock for a company like Meta that is so all in into virtual reality. It's pretty interesting because their whole idea, and even throughout the paper, they mentioned this, it was to use SAM as a sub-module that was very reactive. A bit like the GPTs that are hosted by OpenAI and like whatever. They're very reactive. They can like almost be instantaneous. It's kind of the same idea here. Like they did the setup so that like they could host this and actually make it interactive with a demo of some sort. You can actually like just go to the demo and test it. This whole idea is if you make sure that your infrastructure allow for this, now you can use that thing as a sub-module in whatever kind of bigger system you want to do. So it just happened that Meta is big on VR and AR. A model like this that is able to kind of segment anything and be prompted in different ways to do zero-shot task will be very useful in something like a bunch of ribbons that you have that can understand what the heck is happening in your field of view. So yeah, good business move here. So to make this kind of foundational model possible, there's a lot of structure that need to be put around the model so that it learn the quality of having flexible input and working well under uncertainty, like this one over here, where there's a dot that is put on the stuff. But what does it mean? Does it mean the whole like ostrich, just the top part or just the head? You need to be able to work under these uncertainty. And similarly, to be able to train such a model, if you think about the generative pre-trained transformer, they have like internet scale amount of text data. They had to kind of build their own mass data set, and they were able to do it. And this is what the segment anything paper is not just about the model, it's also about like the data set. So they were able to generate 1 billion masks using like annotator that they had to pay, and then the model also was feeding back into the data, and then they were at some point being able to get to 1 billion masks to train their model properly. So before jumping into the model architecture, let's get a feel about like what SAM1 can do using its zero-shot capability on 2 tasks: automatic segmentation and single point mass generation. We're going to look at a bunch of code now. Here we are in the Collab notebook. This is not too long of a demo because I'm reusing a lot of the stuff that was in their actual GitHub in the notebook section. So, but I just like set it up on Google Drive so I can use it quite easily. First step, we mount the Google Drive, and there we're good to go. And then we can install the segment anything library here. So then I have this section where I'm gonna actually read the 2 images. So one is me in a poster presentation and another one is me in a boat. So let's take a look at that. So this is me in front of a bunch of posters, and this is me on a boat. So the first thing that we're gonna use segment anything for is automatic segmentation. So it needs a few things in there for it to work. Based on the repository. So I need the checkpoint of the model. So I have this one that I downloaded from their stuff and I put into the Google Drive. You have to tell it what type of model you want, because you can have multiple model type and just where the device is in this case. So we're gonna do the SAM automatic mass generator, which will take an image and just like try to segment anything. So our mass generator is created here. So the model is actually loaded. So we have the model here, and then we prep it to do the actual task of like segmenting everything. Now we're gonna take our first image. So the first image was me in front of posters, right? So now we are generating all of the mask for that image. It's done in 11 seconds, so this is good. This thing is just to show the mask in front of the image. So nothing too crazy here, and we're just gonna plot it over there. If you run it multiple times, it will just be different, right? So here's the segmentation that it done. So it's not too bad actually, it's pretty okay, but it just like literally segmented everything in this stuff. There's hair that are well segmented, even though we have different type of hair. The end over here, our coat are segmented. Yeah, it looks not too bad. Now let's take a look at single point segmentation. So basically you put 1 point in there in the image and you try to do the segmentation. And in this case, you will segment with the ambiguity of the 3 parts. So you can have like the sub part, the part, and the whole. So this is just some helper function to be able to actually show the stuff properly in the image. But here we're gonna take the SAM predictor. So this is another class from segment anything. And then we're gonna set the image that we want to do the single point prediction on, and this one will be the boat one. And then here, this is where you're gonna say what is the coordinate of this point. If it was interactive, you will just click on it, and then this will get like fed directly in there. But here, this is manual. And you're gonna see that in the result section for one of the tasks, the first one. So what do we need to segment if I select this? Is it the whole human? Is it just the t-shirt? Yeah, it's a bit ambiguous which part we should segment here. Let's actually predict that and see what the heck SAM can do. So then we can do this. This function is same thing as the previous one, just to show the mask properly, and there's gonna be like 3 masks that we're gonna show. So now we're gonna iterate with the mask and the scores, and then we're gonna just show like the proper mask and the proper score that it got. So let's take a look at this. This one, it got a good score, and you see, wow, look at this clean segmentation of the t-shirt. This is pretty good actually. Wow, I'm impressed. Then there's this one, the second mask. So this was the sub part, right? This is the part which is like, hey, let's actually segment the human. My hair seems to be something. And then like the whole part is, I think, the whole human. Yeah, that's it. So kind of makes some sense here. So anything that is extra to my skin seems to be this for the upper body. I don't know. Yeah. So this one is a bit weaker than this one. Yes, there you can see it in the score, right? It's more confident about this one, the only the t-shirt. This one is less confident, but still pretty confident that like, hey, I think he wanted to get the whole human. This one's like, I'm not sure, but I think like it's the t-shirt plus the hair of the dude. So that's that. This is how you use SAM at a very high level using the code from Meta. Now that we have a good feel about what SAM is trying to achieve and how it runs, let's take a deep dive at the model architecture. So the architecture kind of look like this. So you have your three main block that we're going to see in code soon, the image encoder over here, a prompt encoder over there. We have the code for that. We don't have the code for the text. We'll see why in a minute. And then we have the mask decoder, which is kind of custom because you need to be able to take the image embedding and the prompt encoder, which are, by the way, the prompt are sparse with the points, box, and text, and dense with the mask. And they don't mix together. It's like separated, and then they're combined afterward. So the model resolve ambiguity by just like literally outputting three type of mask always. Three was enough for most use cases, and then you get the score, and then they have like an IOU prediction module that will kind of estimate which one will be the best, and then we'll output only that if needed. Otherwise, we'll always output a tree. So, interesting part, all of these elements, like they're not all novel. Like this part is absolutely not novel. It's a vision transformer, so the H version. This part also is not that novel, especially the clip part, which is the text encoder. The mask decoder is kind of novel, but not that. It's just a transform version of another step. The novelty in this whole thing is really reside on how they set up the infrastructure and then the training procedure, like the generative pre-trained transformer, to have this kind of emergence of zero-shot capability. So if we look quickly at each of them, so the image encoder is a VIT, like I said, it's a mask autoencoder. Nothing too crazy here. The prompt encoder has like really two parts, so the dense part and the sparse part. And the interesting part here is the dense part with the mask that it output. It's really useful when you have to kind of compose SAM with multiple other model like a VIT-H, and they're doing this in the instance segmentation. And then there's like the mask decoder in the appendix to go into more detail about the structure, and we can see that in the code how it's made. But they base this thing into the like transformer decoder block, and they have a modified dynamic mask prediction head that use the prompt self-attention also, and cross-adaptation to update like all of the embeddings. There's also an NLP that is used to output the token to a dynamic linear classifier. So this is tasked to computing the foreground probability at each of the image location. So at a more granular level here, the loss that we're using is there's a focal loss and dice loss at a 20:1 ratio. And the focal loss is designed for like extreme class imbalance, like when you have a lot of background point and very few foreground point. So this is during the training. And then this is effectively just like a modified version of cross entropy. Then you have the dice loss here, which is defined as 2 times the area of overlap divided by the total area. The idea here is like for the dice to put more weight on the right overlap region. So the training algorithm is very crucial and central. It's a central piece of the whole thing because this is how they like mimicked the generative pre-trained kind of setup. It's doing the same thing as when an annotator will do interactive segmentation. So there's a bunch of more detail about it, but like that's kind of the gist of it. And then the actual training recipe, they use LMW, they regularize the SAM with like the weight decay to 0.1, and then they apply drop path. So there's nothing too crazy here in the actual training of it. They use GLU in most of these of the network also. All right. So let's take a look at the main architecture code for SAM and its 3 main components. So I'm going to break down the 4 main blocks in the GitHub repository, and we're going to see like how they're all connected together. All right, so the whole code is over here in the segment anything thing, and if you can see here, there's a subtle link to go to segment anything too. But what we're gonna take a look here today is mostly over here in the modeling section. We're gonna look here mainly at SAM, the prompt encoder, the mask decoder, and the image encoder code. I just split them up and then I put them into like a whiteboard type of application. So here we are. I made a video about how to go about looking at these type of kind of deep learning architecture in the code, and then understanding how you need to navigate them in order to understand them. So you can check the video, but we're mainly gonna go over here and start at them one by one. So let's take a look and zoom in into SAM. At a high level overview, SAM is kind of a wrapper class which will encompass the image encoder, the mask decoder, and the prompt encoder, and it will compose them in order to kind of do the output. You see SAM, the class, doesn't have much because all of the stuff is happening in the other modules. So the constructor is kind of straightforward. We're just gonna have these three main blocks, and then we have these for the normalization that we need to do on the image to resemble how it was done during the training. But there's nothing, absolutely nothing of interest in the constructor. Everything is happening in the forward function. If we just take this out, right, and we look at the input and the output of the forward, it will make more sense what the heck is happening in SAM. This is SAM. So you have the image, it goes into the image encoder, and then you have a whole bunch of stuff that happens. You have the prompt encoder here, the mask decoder, and then we have that output. This is like visually. So in data structure format, the input and the output will be defined like this for this whole thing. The input is over here, and it goes into SAM, and then SAM does a bunch of stuff and output this stuff. So what does it do? It's predict the mask end-to-end from provided image and prompt. If prompt are not known in advance, using SAM predictor is recommended over calling the model directly. So SAM predictor, we saw it in the code stuff that we've done before. Just a wrapper on SAM. This you don't need to know. Let's take a look at the input. We have all of these, and the important part is it's basically this whole part over here. From here to here, it's a list of dictionary. Each index is an image, so you can match them. And then the dictionary is what are the input that you're giving for the specific image, and they include the image, right? So I took it out here. So first you have the image, which is the tensor. You have the original size of the image that you're giving also, because SAM will like kind of downscale it and then upscale it so that you can slap the mask back on. You have these four that are kind of optional. So here you have the point coordinate if you're doing like single point stuff. You have the points label. You have the boxes prompt, so upper and lower corner, and then you have the mask input if you're composing the stuff, like in the instance segmentation thing. And here is saying if you want to output multiple masks or not. By default you will do. That's the input that you're giving, and this dictionary for one is one image, and then you can have like however image you want to batch. What it returns though is also a list of dictionary, and a dictionary will have three things. So it will have the mask. So here is like there's a bunch of masks that will return, so it always return the mask. So IOU prediction, you get that, and the low res logit, you also get that. This is for these core if you need them, and this is for the logit that can be passed as a mask to other iteration in another sub module if you need to compose stuff. So if we go down a bit, we're going to do pre-process on each of the image, and pre-process is simple. It will just take like the pixel mean and pixel standard deviation to normalize the color to look like what was there in the training data. And then here we're just doing some padding so that everything kind of looked the same. That was pre-process. And then we're doing image encoder, and we're putting the input image in there. And then we get our image embedding out. So this is effectively like this part that we're doing. So this image encoder stuff is a vit.h, and it's generally embedding. We're gonna dive into it, but not in very much depth, because it haven't changed much. So if we continue here, we are running this across the image and the embedding, right? Because we're batching the stuff. So if there's point coordinate in the stuff, we're gonna get the points. Otherwise, there's just gonna be no points. And then we're gonna take the whole thing and jam it into the prompt encoder. Everything we have, points, boxes, and mask, we give it to the prompt encoder, and then the prompt encoder will kind of figure how to wrangle the sparse and then the dense embedding. So this is what we get out, sparse and dense. So this is this part, right, over there. We've done this part. And after this point, we're gonna do the mask decoder. We're gonna take like everything that is our current embedding, the prompt encoder, the sparse embedding, all of this. and we're gonna give it all to this thing, and then it will go here, and then it will go through this complicated flow to output the mask, the IO score over there. So this is what we get out, the mask and then the IO. Here this is low resolution, and we're gonna post-process them to upscale them back to what they were supposed to be. So this is the post-process mask, which is over here. You give everything. So remove the padding and upscale the original image size to interpolate function call here to do just that, to remove the padding and then to upscale them. And that's that. And after that, what we're doing is we're thresholding the mask, right, with this mask threshold variable, and we just output that in a dictionary. You see, you have the output here. This is a list like that. So this is how we output list, and we go and iterate into one image at a time. Let's take a look now at one of these components. First one we're going to take a look at is the image encoder, and the image encoder, like I said, is just like straight up ripped from another part. So it's in this this backbone over there in the Detectron 2 repository. So literally took it, modified a bunch of stuff, but not too much, and then just jam it in there. So if we see over here, this is the image encoder vid class, and there's a whole bunch of variables. Most of them are already like pre-put. There's not that much that we need to know. The activation layer is all JDLU. We have the normalization layer that we're using. This is another utility class, but like it's not that important. And all of these parameters match what is supposed to be based on the data set that they're running with. So here they're constructing the network, and it's fairly straightforward. You have the patch embedding over here, and then if we're using the position embedding, so initialize them, and after that it's actually building the network. So we have these block stuff, which are the transformer block that were needed here, and then you have like the sequential head. There's two convolution that we're doing: convolution, normalization layer, another convolution, normalization layer, and then we're kind of done. And the forward is also very simple, right? So you're getting the embedding, you're adding the positional embedding back, and you iterate over the block, transform a block, and then you just get out and then do this last part with the convolution layer. So then we're going into the prompt encoder, bunch of parameters to start with, but most of the action is happening here. So this is the position embedding layer that they're going to use. This is for the point embedding over here. There's this embedding for when the point is not there. Here you're using the same trick again when there's no mask added. And then here this whole stuff is to downscale the image, not the image, the mask, just so that they match. Alright, so let's take a look at the forward. In the forward here, we're gonna like embed the different type of prompt, and then we're gonna have two classes. We have the sparse embedding and then the dense embedding. Dense is just the mask that we're gonna return, it's denser, and the sparse is the point boxes and text, but text is not added in this. And that's that. Like if there is a point, we're just gonna jam the coordinate, the labels in there, and our embed points, which will create an embedding, put it over here, and then we're just gonna concatenate it to our sparse embedding. And if there's box, we're gonna do the box and then just embed it. Nothing too crazy. Mask is the same thing. If there's no mask embedding, we're just gonna like use the no mask embedding that we've created over here for this specific purposes. And we're gonna return both of them over here. So embedding, like if you don't know, you should know, but if you don't, so you take something like this that can have a lot of degree of freedom of stuff that it can, how it can be represented. It's that in this case it's a text, but it could be like a mask, it can be like points, and then you find a representation that is in a set dimensional space. In this case, it's let's say you don't have that, it's 3-dimension and it's a vector. So this vector now means angry. So we can go into depth into like what's happening in each of these, but it's not that relevant. You just understand that like for each of the different type of input prompt, they will put them into like a vector space that makes sense for them. Sparse and dense are separated, and here we're just jammed the when we call embed mask, we actually just call mask dot downscaling, and we pass through the network we saw earlier. So yeah, the tech stuff is not there, right? So I checked and I was a bit confused, and I knew it was using clip, but I thought it would, like, I don't know. I actually didn't know what to expect there, but they just didn't add it into the stuff. It's not publicly available. I don't know why. It's a bit weird. Like, I think it kind of sucked a bit. It was not that performant, but it was cool, but not that performant, because they just give one example and like get it wrong. So we have whale, a beaver, tooth grill here, but then when you say wiper, it kind of just doesn't know what you're talking about for this specific image, and you have to click and give a point. So I feel like that specific portion was not as mature and it was not working that well. So this one, yeah, I have to buckle up a bit because it's not the cleanest one of the three, right? It's the worst. There's a lot of layers of complexity in there, but we're gonna unpack it step by step. So here you have the class, the mask decoder class. There's a bunch of variables that are of our interest, especially this one, the transformer one. So you see transformer, it's a module, and then you see it being instantiated here. Self.transformer equal transformer. If you look in here, right, at the top of the file, there's nothing that is being imported here, which I think is a big mistake. Note that, because we're gonna go through like the higher level code, but then we are gonna have to do a bit of a detective work here to find where the transformer is at. You have the rest is, we're just instantiating the embedding for the output. So there's nothing too much here. Here it's the output scaling, that thing, this conf transpose 2D and then conf transpose 2D again, is this part of the drawing over here. And then we have this hyper network over there. It's a MLP, right? And it corresponds to that part here. This one, the IO prediction head, is just one MLP and it's over there. And this one is to estimate the IO score so that we can sort the stuff. So we have these three components. In the forward function, we'll most likely work with this part here. This part, the rest is a bit hidden. We'll dig it. So if we look at the forward now, so you have all of these as input, like we saw in the previous call. It's a bit of a weird abstraction. I don't know why they did that. Maybe they reused some part to say the predict mask somewhere else, but nothing is happening here. There's just a predict mask function, which you give everything, and it give you the mask and the IU pred. The predict mask corresponds to this whole orange box. This whole thing is the predict mask. And then we can do correction if we want to output one or multiple mask. And all of this is being outputted here. Everything is happening in predict mask. So you see already we're starting to go a bit deeper. So this is predict mask, and it's a bit of a mess, to be honest. Here we have the output tokens. So this is these ones over there, the output tokens and the prompt tokens that we need here for the IO token weight. So this will correspond to the like output token over there. So we concatenate all of them together, and then this is this input. The image embedding is here, right? This corresponds to this, but we need to kind of rework it a bit. So this is what this part is doing. It's reworking a bit dimension. These things, so the SRC and the position SRC here will be given to that dotted line setup. Anyway, so we give the SRC and poster SRC and these tokens, right, which are these input to a transformer, which is what we saw before. And this will return two things. It will return this and the SRC. This is, it's over here. This is the SRC, right? The how is it called? HS is here. It's already weird because this thing returned two things that are being the output of different elements in the same architecture. A bit weird. We're gonna dive into it a bit, but then you take these out, the IO token, the mask token, and then we follow like the rest of the stuff. So this SRC that we've talked about, this one will get put into the output scaling. The output scaling we already talked about. It's this one, and then that part over here, this whole thing there is what's happening on over here. There, and then this part here is our dot product per mask. You see we're looking at the upscale embedding, which is gotten by shoving SRC in the output scaling and getting the upscale everything back. And then we do the dot product with the hyper in here, which is when you shove the mask through this network. And finally, the IO prediction head is pretty easy. It's this IO output token, and we are able to create the score here. You see these two things, output token per mask and IO output token. They are within the HS variable that we've talked about, and that is being sorted out over here. Now, most of the important stuff is not being mentioned here. It's just a transformer. So like we saw over here in the mask decoder, there's no transforming being added. So you have to dig a bit. And once you dig a bit, you realize that it's in the init.py of the modeling folder. It's still valid. It's still okay. It's just a bit weird. It's just a bit weird to do it like this. There's a file called transformer, which hosts the two-way transformer. That thing is what's being used as a transformer. In.py will import all of this in all of the file when we're running it. So this is what we're looking for. So you have to take a look actually at the transformer file here. And in the transformer file, this is where we have like the right information about this last bit that was kind of hidden. So the two-way transformer, we get the MLP block and whatever. And then here, this is how it's set up. If you dig some more in another file in the build section, there's something called build SAM. And when you look at it, this is like a way to like build SAM, because you're gonna give it explicitly which part that you want, the image encoder, the prompt encoder, and mask decoder. And over there, then you start to see what's up. So the parameter that is important, depth, has a depth of 2, because it's like the 2 block that we saw times 2. And then you have the other variable that are being set. Now, when it's going to be created, it's going to be created properly. And when you're going to pass the parameters, it will go in the forward properly. Just on the side. So if you look at this and you see no default parameter, don't freak out. Now we're over here, right, in the two-way transformer. And now it starts to make sense, right? So this is 2. The depth, because we're doing from I in range depth, and then we're doing 2 times this. So this is why there's a explicit 2 in here to match this 2 over there. That part, we're gonna go through it in a bit. But this part, the final attention token to image, is this part. If we go a bit down in the forward, here's what's happening. We're very deep now, and it starts to get a bit abstracted away what's happening. But don't worry too much. Here we're just normalizing a bit the format of the stuff. There's 2 things that are important, the queries and the keys. The queries are these output, and the keys, these output that will be out over here, right? So we're putting the queries and the keys, which are the point embedding and the image embedding. So the keys are the image embedding, the queries are the point embedding, and then we're gonna shove them through the layers. So through this layer over here, there's 2 of them. You see the keys get changed and the queries get changed. Now, that's this part, right? This is this part. So this part over here only get applied to the queries, actually. If you follow this part, we're changing a bunch of stuff over there. And then we're running the final attention token to image, and we're passing the Qs and the K here. And then we're passing also the keys over there. And if you take a look, we are changing the queries here. The queries get modified, and only the queries goes through the final normalization layer. So the queries get overwritten on this final layer, but not the keys. The keys are the same as these ones. So this is how we get the keys, which is the SRC variable at the top that we saw, and the HS variable kind of separated. We overwrote this when it went through this, right? We overwrote it, but here we didn't overwrite it. We just returned it as it's skipping this final step. Now, this layer, let's take a look at it. This is a 2-way attention block, and if you take a look, we have the attention. You can dive to how attention is set up, but this is fairly standard. So there's an attention block over there, and then we're naming really well the stuff. So here, this is a cross attention token to image. This token to image is this one, right? And then we have our self attention here. This layer is this one. Then we have normalization layer. We have our MLP block over there with normalization layer. And then we have our cross attention image 2 token. So this one is here. Remember, this is one of the block. There's actually two of them when we're out of there. But here, there's only one. And if we look at the forward, also pretty standard. We're taking the queries, which is the purple thing here. So like this is our prompt stuff that goes there. And then this is our keys that are going over there. So this is cross attention block. So token to image is this one. And you see we're giving the both the keys and queries over here. And then the self attention, we have given it over here or there, depending if we're skipped layer, whatever. So this is happening over here. There's no key that is being added. MLP block, this is happening here. And then cross attention image token, this is happening over there. And that's it. This madness stops here. But you see how deep we had to go to just go back all the way up over there in this transformer thing. Honestly, this predict mask, we shouldn't have needed that thing, right? Depending, I don't know, I didn't dig deep enough, maybe I'm wrong, but like this layer of abstraction for me is absolutely useless. It should stay in the forward and be jammed as is, because then we're too deep. The second thing I think they should have done is actually just import the thing in there. Worst case, you import it, and now it's just more clear. It's a two-way attention thing versus just like, it's just transformer that is being mentioned here. The third thing that they did wrong, well, not wrong, but I mean, they could have done better, is on this part, like, just put some default. They were doing it in all of the other thing. Just put some default that look like what you said in the paper. Yes, maybe like you need to change some stuff depending on the experiment that you were running. But if this is like one of the structure for the paper, and then it's literally a figure that you're having that is this, please do put it as a default. It will be easier to follow the flow because I had to do like some intense detective work to be able to figure out what the heck is going on. Anyway, that's the mass decoder. So now if we come back all the way up to SAM, when we do mass decoder, we did all of this stuff. When we do prompt encoder, we did all the stuff that we saw. And then when we do image encoder, we did the vid stuff that we saw. And we just compose all of this together and then we shoot it back to the output. Now that we have a solid understanding of the internal architecture, let's take a look at the other important part of SAM, which is the data. Datasets wise, SAM 1 is absolutely massive. So it's order of magnitude greater than like the other mass dataset. So you see here we have 11 million images. And then you see the other ones, like there's just open image that get close to the number of image, but mask wise, it's order of magnitude greater. 1.1 billion mask for 11 million images. And if you see here, there's generally more mask per image with SAM. So if we look at the percentage of the image that has mask, we see it's not like super bulky ones. It's a bit more precise, less bulky than the other ones. And if we look at the percent of a mask that has like very high complexity, it's like similar to other dataset here. And by the way, the dataset is open source, so that's pretty cool. So if you want to take a look at it, you can take a look at it in the website. How they were able to train something like this is very interesting because they leveraged the model itself and human annotator to build up an actual dataset. So the first stage here was assisted and quite manual annotation. So it was just to build the initial dataset needed for the next stage. So this is purely classical assisted segmentation methods, nothing new here. The second stage is where it gets interesting because the model at this point was good enough to get the big mask going in each of the image, but the author wanted to add a bit more diversity in the type of mask generated. What they did was a semi-automatic stage where the annotator had to fill up the rest of the smaller objects that were not detected by SAM, which was pre-filling all of the image with like the big mask. During this process, they retrained the model multiple times, so it got better and better. So at this point in time, they had like millions of masks already built up, and then they retrained SAM1 on all of this. In the third stage, they just let loose the model completely on the whole dataset and generated billionth worth of masks. This was feasible mainly because At this point in time, the model was good enough and it understood ambiguity because of its architecture. So using no maximal separation and other thresholding technique, they were able to gather like the most confident mask on all of these 11 million images. And in each of these images, there was like quite a lot of masks. And this is how they got a billion masks. With these three components working together, the other were able to create that financial model. Let's take a look at the result now. First one we got is the zero shot single point valid mask. This one is difficult because the answer is very ill defined. It's a single point. There can be multiple answers to that point. The other tested their performance of their model on 23 dataset, which did better in 16 of them. Interestingly, when they ask human annotator to rate the mask, those of SAM1 are always coming on top, just below the ground truth. Another cool thing is that SAM1 is better than other algorithm when there's a lot of ambiguity involved. With 1 point, it gets consistently better result across dataset. Next up, we have the classical task of detecting the edges on an image with the BSDS 500 dataset. Reminder that SAM is simply being prompted properly in here to be able to generate the right output. So specifically, they prompted SAM with a 16 by 16 regular grid of foreground points. They removed the redundant mask, use Sobel filtering to unthreshold the mask probability map, and then they do some other post-processing to get the final result. And if you look in the image, it does look qualitatively good. SAM is not the best in this specific instance, but is the best of the zero-shot transfer method. A reminder here that SAM never saw the image in the BSDS 500 dataset compared to the state of the art. Afterward, we have the classical task of object proposal. The visual transformer .h version is obviously better than SAM since it has been trained on the Elvis dataset in this case. The other are hypothesizing that it has learned the idiosyncrasy of the data while SAM didn't have access to it. What we mean by that is all the little details that will game a bit the performance metric. Interestingly, SAM is doing quite well in medium and large mask. It's really in a small object to detect that it struggled a bit. Next up, we have the instance segmentation task where we're trying to make a pixel by pixel segmentation map of everything in the image. So basically segment everything. The method is interesting here because it uses the same combination methodology that we see in systems like DALI with the clip model inside. So here the vid date is prior to being fed to the SAM model. You can appreciate qualitatively how SAM is able to improve the quality of the segmentation based on that vid.h mask input. Quantitatively again, a trained vid.h model on the Elvis dataset does better than just SAM, but when the human annotator look at the quality of the mask, SAM look better and closer to the ground truth. Finally, the other did something very interesting where they tested the zero-shot performance of SAM on a null task of text to mask. There is no quantitative result here, just a qualitative one, and we can all admit like pretty cool. The one thing that is interesting here is that when there's a mix of text plus point, the model is improving quite well. So result-wise, we see that SAM has some interesting zero-shot performance. However, there are some limitations with this first iteration of the segment editing model. So as explained by the other himself, like it's not perfect, can miss fine structure, hallucinate small disconnected component. It's not as crispy as other more fine-tuned method. They are saying themselves that there's room for improvement in the general architecture, but also generally just the performance of the model. So with more effort on this front, this whole technique can be much improved. Which is exactly what happened all throughout 2023 and culminated with SAM2 that was released recently. With FastSAM, the one thing that the other realized was that they could remove the transformer backbone and instead use a regular CNN YOLO V8 detector with the instant segmentation branch. With that change, they were able to have like a 50 times speed up at runtime, and you only need to be trained on 2% of the 1 billion mass dataset. Mobile SAM then applied knowledge distillation to compress the overall size of the SAM network. With this knowledge distillation protocol, mobile SAM was able to get 5 times speed up on fast SAM while being 7 times smaller. The knowledge distillation happened mainly on the image encoder portion, which is the heavy part of the model. You can check out here qualitatively the difference between SAM, mobile SAM, and fast SAM. All three methodology give seemingly similar result, with mobile SAM having performance that are most similar than SAM. The improvement is kind of bonker here, with mobile SAM 100 times smaller than SAM, 200 times faster at inference, and of comparable performance than the original one. The power of distillation technique here can really be felt. This distillation trend continued with efficient SAM, which use it at its core to yield even better results. SAM2 is a whole other beast. The important part here is that this rapid progression from the initial idea of SAM, it's showing the kind of clear trajectory that was already seen in GPT-based model with natural language. So if you build a foundation model with abundant data and with zero-shot capability embedded in how it was trained and how it deal with ambiguity, then there will be like a flurry of improvement on the model capability, which is exactly what we saw with the SAM family of models. So I truly believe like the next stage for AI in all of the different subfields, they really will have these models, these foundational models that are very flexible at their core. That's it for today. I hope that you enjoyed the video. Don't forget to like if it was the case and leave a comment if you have any question. I'm here to help. Have a great week everyone and see you in the next video.